We'll start with what is becoming a fairly familiar procedure by now, and that is we're going to take a spherical shell at a distance little r from the center of the star. It has a density rho of r, and we're going to say that in this spherical shell there are nuclear reactions going on that are generating energy at a rate given by epsilon r. So this is the rate of generation of energy per unit mass. So in other words, every kilogram of matter inside the spherical shell is generating energy at this rate. Right? So it has units of watts per kilogram. Now, we want an equation for how the luminosity changes. Now, luminosity, you can define the luminosity anywhere within the star. We usually think of luminosity as the rate at which radiation energy is coming off of the surface of the star, but radiation energy or other forms of energy are moving through any given point in the star all throughout the star. So at any point in the star there is a luminosity, and rate at which energy is being transported outwards at that point. So if energy is being generated in this slab of material, then it's going to increase the luminosity by a certain amount dl, so that when you come out the other side of this spherical shell, the luminosity is L of r plus dl. Right? The luminosity has been increased because you've released some energy from nuclear reactions at this rate. So we can just write down an equation. Essentially, this just comes from the definitions of the quantities we've laid out here. If the energy generation rate per unit mass is this, then the total energy generated in the spherical shell is going to be this multiplied by the mass of the spherical shell, which is its surface area times thickness times density. And this has to be equal to dl, the amount of energy you've added in this layer. So if you divide through by dr, you get our next equation of stellar structure. Dl by dr is equal to 4 pi r squared epsilon of r rho of r. Okay, so this is the equation of energy generation. So this energy generation, as we said, is going on in the core of the star. So here's a cross-section through our sun, and the input into this equation comes from the nuclear physics of the situation through this energy generation rate here. So how is this transported outward? So in the textbook, there are two equations that are derived representing the two ways in which energy is transported out inside of stars. In general, there are three ways of transporting energy. There is conduction, convection, and radiation. Conduction is very efficient in solids, but stars are not solid. Conduction is very inefficient in stars. So we only have to deal with radiation, in which the energy is transported out by the photons. And in the sun, this is most efficient in the large region of the star above the core that goes from about 1/3 of the way out to 2/3 of the way out. And the equation for energy transport by radiation is given here and is derived in the textbook. And one can express it as an equation for the temperature gradient, the rate at which the temperature inside the star changes. The temperature gradient is negative, which means that the temperature is decreasing as you move out from the core of the star. However, in the outer third of the star, it turns out that energy is transported more efficiently through convection, which is a different physical process. This is where energy is transported by bulk motion of matter in large circulatory patterns. And so the equation of energy transport is different and has this form here, and gamma here is the adiabatic index that we encountered in the equation of state. How can you tell which one of these is going to happen at any point in the star? Well, what you do is you calculate both of these equations, and whichever gives the larger temperature gradient at any given point is the transport mechanism that occurs in the star. Now, in the equation for energy transport by radiation, there is a very important quantity represented here by kappa called the opacity. And I just want to say a few words about what opacity means physically. So to give you some idea of what the optical depth means, and maybe a little bit of insight into it and how it's related to the opacity. Let's say that energy is being transported out from the center of the star to the surface of the star, and it's passing through a layer of matter. So we have luminosity coming in and some luminosity coming out. Now, if we're in a layer that in the outer layers of the star where energy is not being generated, then the luminosity will in general decrease because it is being scattered or absorbed by this layer of matter here, which, let's say, it has a thickness dr. So the fraction of the luminosity that is lost here is just dl divided by L. The opacity of the material is defined to be, we use the symbol kappa for the opacity, and it's defined such that the fraction of energy lost by the matter here is minus the opacity at this point in the star, multiplied by the density times the thickness of this layer here. So what this essentially is the fraction of energy lost per unit mass in a given, over a given area, cross-sectional area that the energy is flowing through. This equation is a definition, right? The reason for this equation is that we define kappa so that this equation works. Right, so this is entirely something, a quantity that we have invented because it is a useful quantity to describe essentially how much radiation gets absorbed or scattered by matter as it passes through. This quantity here, dl over L, we can call d tau, which is known as the optical depth. And what this essentially tells us, it gives us an idea of how opaque the matter is, how far, if we look from up here inwards, then how far into the material can we see? How transparent is it? If it's equal to 1, that means dl is equal to L, right? Or in other words, there's zero luminosity coming out the other side. So all of the radiation is getting absorbed or scattered here, and none of it makes it to our eye. So this means that the material is completely opaque. You cannot see any distance into the material at all. And conversely, if it's 0, then none of the light gets absorbed or scattered. All of it makes it through to our eye, and the material is completely transparent. Okay, now let me give you a little bit of information about the processes that cause opacity. What causes light to get scattered? Well, it's because this matter is made up of atoms, which are made up of electrons and protons and neutrons, although neutrons are less important. And photons scatter off of electrons and protons. And so they can be absorbed or they can just bounce off of those charged particles. And there are a number of ways in which they can do this. And the most important three are as follows. There is so-called bound-free absorption or scattering, in which a photon, which we always depict as a wiggly line, comes in and encounters an atom which still has some of its electrons attached. It hits the electron and knocks the electron out of the atom, leaving behind an ionized atom. So that's bound-free absorption. Okay, in other words, the electron is going from being bound to the atom to being free of the atom. Then there is free absorption, in which an electron which is still influenced by protons but is free has been ionized, but is still traveling in the electric fields locally created by these protons. Well, what happens is this can be thought of as in a gravitational analogy, as an object in an orbit that isn't elliptical around another object, so such as a parabolic or hyperbolic orbit. So such orbits are free, and the object is not bound to the thing that it is orbiting. So this is a similar situation, and the photon comes in, hits the electron, and knocks the electron into a different but still free orbit. So the electron starts out free, ends up free, just with a slightly different motion, still under the influence of nearby protons. In both of these cases, the opacity is proportional to the density of matter times temperature to the minus 3.5. This is a result that comes from atomic physics. This is one application of atomic physics. And then the final process that will be important is Thomson scattering. And this involves electrons that are so high energy that their influence by protons is completely negligible. So they are the freest electrons can possibly be. And it simply involves a photon coming in, hitting the electron, and bouncing off of it, giving some of its energy to the electron. And the opacity in this case is constant. This happens when matter is highly ionized, which tends to happen when you have hotter stars. So these tend to be important for cooler stars. This tends to be important for hotter stars. So let me summarize the equations of stellar structure to see where we've got to. We started off just deriving the law of mass conservation, a very fundamental law in physics, and then the equation of hydrostatic equilibrium, which just tells us the pressure pushing outwards balances gravity pulling inwards inside of a star. The equation of state connects the pressure with the density and the temperature inside the star, and the physics behind this equation is simply that the pressure arises microscopically from atoms or ions bumping into each other. This is so-called thermal pressure. Energy is created in the center of the star, so we derived an equation to reflect that, and it is transported out to the surface of the star via either radiation or convection or some combination of the both of them. The input into these equations comes from nuclear physics and atomic physics via the energy generation rate, epsilon, which is calculated using the physics of nuclear fusion, and the opacity in the star, which is calculated using what we know about atomic physics. There are also always going to be some free parameters in the model that we don't know ahead of time. The mean molecular mass, which tells us the composition of the star, we don't know ahead of time. We don't know quite what chemical elements are there in the interior of the star. So what we do when we solve these equations is we guess values for the mean molecular mass, and we pick the ones that give solutions to these equations that agree best with the physical properties of the sun or other stars. Once we've set these parameters and we've got these equations, we can solve them and we get how the pressure, the mass, the density, the luminosity and the temperature of the star varies from the center of the star to the surface. And there we have our basic model of a star. Now, of course, solving these equations is in general a little complicated. This is a system of at least 4 coupled differential equations. But as we'll see next week, we can actually make some very useful order of magnitude estimates using these equations that will actually give us all of the basic physics behind stars and allow us to explain the Hertzsprung-Russell diagrams that you yourselves have plotted. So that's what we'll be doing next week. We will be using estimates based on these equations to examine whether our physical model can predict what we observe.